everybody. This is the flash session 1 on COVID, congestion, electrification, and more. And my name is Krishnan Viswanathan. I'm a principal at Cambridge Systematics. I do work in data and modeling. And we have an exciting session for you. We have a variety of speakers talking on different topics like transit, COVID, electrification, and things of that nature. And so this is the agenda. We have around 8 presenters, and the authors are bolded, and the authors are going to present their names have been bolded. And so with that, the very first speaker is going to be Maximiliano Lizana. Maximiliano is a Chilean PhD student at the Institute for Transport Studies at the University of Leeds in the UK. And he's supervised by Professors Choudhury and Professor David Watling. His main areas of interest are travel behavior analysis and transportation modeling using big data sources. And he's going to talk to us today about his research, which aims to identify and model mobility profiles of public transport passengers, considering the changes in their travel behavior after a critical disruption in mobility caused by the lockdown in Santiago, Chile during the early stage of the pandemic. And with that, I will stop sharing my screen so that Max, you can take over.
Fantastic, thank you very much.
I can figure it out. All right, go ahead, Max. The floor is yours.
Thank you. Okay. Well, thank you very much for the introduction. Let me change this. Okay, my name is Maximiliano Lizana. I am a PhD student at the Institute for Transport Studies at the University of Leeds. Today I'm going to present part of my research related to the effect of COVID on public transport demand, which I titled Clustering Approach to Investigate the Impact of the Pandemic on Public Transport Usage using smart card data from Santiago de Chile. Okay, let you know, public transport is essential in people's daily life. It plays a crucial role in integrate the different parts of the city with their citizens, and also it is the most efficient mode to move massive volume of passengers. However, after the outbreak of the COVID-19 and led by mobility restriction, change in pandemic and related to the different pandemic stages and risk perception, severe change in people's travel behavior and the perception toward this mode has been generated. So to rebuild part of those adaptations, we propose to characterize a profile of public transport passengers, considering the change in the travel behavior during the pandemic and after the lockdown in the early stage of the pandemic. In particular, focusing on analyzing different dimensions of travel behavior. So we chose Santiago, Chile's capital, to illustrate the impact of COVID-19 on public transport demand. Santiago has a population of around 7 million inhabitants and manage a complex public transport system that integrates the urban bus, the underground that is called metro there, and the light rail also. The payment system consider the use of a smart card that gather information in each transaction related to the ID of the car, the timestamp, the mode, and the boarding station, for example. So here I am showing the variation in ridership in Santiago public transport system from January 2020 to June 2021. To illustrate the change in public transport demand, we propose to consider a period of 2 weeks to illustrate key periods. So here I am showing the period analyzed for illustrate the travel behavior characteristic from the pre-pandemic. We analyze here the first 2 week of March 2020, and for the opening 2 weeks of November 2020. This opening period followed an extended lockdown in Santiago that lasts several months. So the methodology include a 3-stage approach based on disaggregate smart card data transactions. So first, we estimated in the first step the residential area of each public transport user. In the second step, we carry out a clustering analysis after estimated 8 different indicators that capture the interpersonal travel behavior chain for each passenger. The outcome of this clustering analysis is the assignment of each passenger to a unique cluster that is associated with homogeneous passenger around each cluster. So the last and 3 step is the modeling of the membership of the clustering found in the previous step, and the association of that class membership specific with some explanatory variables. So using disaggregate smart card data records, 8 different indicators were estimated to illustrate the public transport usage chain. So this is very important because in the previous literature, the most specific mention is related to one variable independently. So in this approach, we use several indicators to illustrate the chain in public transport passenger. Some of the variables that we use were, for example, related to trips intensity, transport mode, temporal patterns, and spatial adaptations. So for trip intensity, for example, we use the variation in the number of trips. For temporal patterns, the variation in the average departure times. And for spatial adaptation, we estimated a location similarity index. For time, I'm going to show only 3 variables here. But for a clustering analysis, we implemented k-means, and for find the proper number of cluster, we use the elbow method and the silhouette score. Here I am, before that. So using the elbow method and the silhouette score, we found that the optimum was to cluster, okay? So here I am showing the some box plot related to 3 of the 8 indicators used in the clustering analysis. So in the first one, the graph illustrated the distribution for the variation in the total number of trips. Here we can observe that for cluster 1 and cluster 2, most of the public transport passenger analyzed experience a negative variation. So that we know about that, of course, yeah. And however, if we can observe only cluster 1, the median was only -2 trips compared with cluster 2 that shows a median of -14 trips. So both clusters are completely different in terms of trip intensity. Another thing that is interesting here is that in cluster 1, we can observe that at least 25% of the members that are in this cluster carry out more trips during the opening than the pre-pandemic. Related to the variation in the average boarding time for first trip, we found that the median for the cluster 1 shows no variation because the value was close to 0. But for cluster 2, we have that 75% of their member exhibit a delay in their first trip during the opening compared with the pre-pandemic. Additionally, a location similarity index was estimated to measure how similar was the boarding location between both periods for each passenger. So a location similarity index of 0 indicate no match between both periods, and a location similarity index of 1 indicate that the boarding location identified in both periods were exactly the same. So for cluster 1, we can see that 50% of the members have a location similarity index above 0.5, but for cluster 2, 75% of the members have a similarity index below 0.5. So we can see here a distinctive difference between both clusters. It seems that cluster 1 are made up of those public transport passengers who tended to return to the pre-pandemic public transport user, compared with the cluster 2 that are, it seems that are made up of those passengers that exhibit the most extensive chain. So we use a tag returners to call the member of cluster 1, and we use the nickname of adapter to call the members of cluster 2. So the next step and the final one was modeling the membership of public transport users to these two clusters. And this problem is a typical binary classification that can be addressed through, for example, a binary logistic regression, where the dependent variable are the cluster found in the previous step. So if in particular, a certain passenger belong to the returner cluster or belong to the adapters cluster, and the explanatory variable that we use were grouped in 3 different type of variables related to their travel history, their car type, and socioeconomic characteristic of the areas where each public passenger live. So the result of the binomial logistic regression shows that some variables related to travel history were positively associated to the returners cluster. For example, if someone carry out more trips during the lockdown, or has more trips on weekend and day traveling during the pre-pandemic, those public transport passengers had a higher likelihood of belong to the returner cluster. Also, some equity issues were detected. For example, some the passenger who show a higher average travel time and to live in areas with a higher share of immigrant and workers also were related to the cluster of the returner, those that return to their initial pre-pandemic public transport use. By contrast, related to the adapters cluster, we found that the number of trips on weekday in the pre-pandemic and the higher share of women in the areas where they live, or the university educated population in that area, were associated possibly with the adoption of the adapters strategy. So to sum it up, we found that the recovery in public transport usage was heterogeneous in those passengers who continued traveling between the pandemic and the opening period. We found that 14% of the total user increased their number of trips during the opening compared with the pre-pandemic period. And also we found some inequality issues that were associated with the cluster identifier. Thank you very much.
Thanks, Max. Anybody has any questions for Max? If not, I have a clarification and a question. The clarification is on your box plot.
Sure.
This one. Can you explain this boarding time? I didn't understand that. The variability in average boarding time.
Oh yes, yes. It's related to the first trip of the passenger. So here, in the y-x, it shows that if it's positive, they start their trip during the opening later than the pre-pandemic. So here, for example, my point was that now we have here that cluster 2 are those that now are traveling maybe 2 hours, 3 hours, 5 hours later than the pre-pandemic. So if we analyze, for example, and aggregate demand of bus station, we can observe that now maybe the AM peak is not between 7 and 8 a.m. Maybe it's now 30, 45 minutes later than that. That is the mean of that.
Okay. And the other question I had was, was income not a significant variable in your logistic regression?
Yeah.
So, because I do notice that, immigrant workers and university educated kind of correlate with income, but I was just curious. So income wasn't a significant variable, I'm assuming.
No, the problem is that we don't have information of income in our database. Indeed, the only disaggregate information available in our data is the type of car. If the person was like a senior or an adult, but there is no more. So the way that we introduce socioeconomic characteristic here was through the identification of the residential location of each passenger. So we use, it's not mentioned here, so thank you. We use the information of the census, but Chilean census doesn't consider explicitly the information of income. So they use it's possible to use maybe, for example, level of education, something like that, but it's not, there is no information sadly about income that, like I said, is very important. And we think that now part of that effect is considered now in the university educated. But in terms of the higher university educated population in some areas, people, the passengers that live there, it seems that is more free to adapt their behavior after the lockdown compared with those that do not live in an area with the same characteristic.
Okay, thank you. Anybody else has any other questions? If not, we'll move on to our second presentation.
Thank you very much.
That's by Matthew Daus. Mr. Daus currently serves as Transportation Technology Chair at the City University of New York's Transportation Research Center, and he conducts research and continues to be extensively published as an expert in ground transportation regulation and technology. As a CUNY distinguished lecturer from 2010 to 2018, he has taught courses on transportation history, policy, sustainability, for higher regulation, and technology. And Mr. Daus also continues to serve since 2009 as president of the International Association of Transportation Regulators, a non-profit educational peer group of government transportation regulators from around the world, promoting best regulatory and innovative practices. So Daus is the longest serving commissioner, chair, CEO of the New York City Taxi and Limousine Commission, where he served from 2001 to 2010. And prior to this tenure as commissioner, he served in many other executive positions and council positions in the New York City government for almost 20 years. He currently is a partner at Windelsmark, Lane, and Mittendorf LLP, where he founded and chairs the transportation practice group since 2010. And his presentation is going to discuss the post-pandemic rebound in traffic congestion in the US and its underlying causes. And he's going to follow that up by an enumeration of the International Association of Transportation Regulators guiding principles for congestion mitigation. With that, I'll turn the floor over to Matt Poss. And I just forgot to mention one thing, like we are trying to, because there are 8 presentations, trying to keep it to 15 minutes with 12 minutes for presentation and 2 or 3 minutes for Q&A. So hopefully we'll stick to that.
Okay, I will try to do that. Thanks for that introduction, Krishna. It's good to be here. I assume you can all see my screen now?
Yeah.
Great. So this is a submission which I thought was important for this conference because it's more policy directed, and it's talking about what some of the regulators are planning to do, which may guide further research for many of the people attending this conference. And it's kind of looking at the big picture post-pandemic in terms of congestion mitigation and talking a little bit about our group and what we plan to do. So let me just try to get to the next slide. Well, we already talked about my bio, so we'll get right into it. I think we all know that transportation is a large part of emissions, and it needs to be tackled and under control. And things have gotten worse. Less people are using public transit since the pandemic has happened, continuing to this date with work from home issues. And everybody spoke during the pandemic about Carmageddon. Well, it's here already. We already are now experiencing traffic congestion all around the country at increased levels with queuing on public roads. And we in New York, for instance, just as an example, subway ridership was just 57% of what it had been. Office occupancy stood at just 41% at the end of June recently. So people are not coming back to work in their offices. They're working from home still. There's a lot of issues that go a little bit beyond the pandemic, including crime in the subways, which in New York is a particularly daunting issue, which is making the depressed ridership even worse. People are fearful of getting on the subway. We've had mass shootings and incidents that continue, and there's a debate raging right now as to how we solve these issues. So it's crime, the post-pandemic fallout, and there's an increase in BMT, as you know, and traffic volumes are already back in most major cities. Getting at some of the root causes. I think there's plenty of research and theories out there about what is causing the increase. We do have, I think, a milestone of new car registrations reaching a 10-year high, which I think was fueled by the pandemic for sure. For-hire vehicle growth, that includes the ride hails that are out there over the last 10 years have grown significantly. We used to have a very limited number of taxis and for-hire vehicles. Now the numbers of vehicles on the road, whether they're owned or leased, are off the charts. It's not a major factor, but it is a factor. 2 to 13% of the VMT are ride-hail vehicles. And we just throw out there that the World Economic Forum found that the growing demand for delivery could spike congestion by more than 30%. It's already up, as we know, post-pandemic and during the pandemic, and that is a trend that's likely to continue as time goes on. So at the ITR, we are a group of regulators. I used to be the taxi commissioner, but we have taxi commissioners and now TNC commissioners that regulate Uber and Lyft that are all over the world that are members of our group. It's a nonprofit. We hold conferences every year. And one of our things that we do is we develop guiding principles and best practices and model regulations in different areas. And we felt in light of what happened with the pandemic, and a lot of the movement towards sustainability, it was time for us to put out some guiding principles for policymakers in the transportation field, for them to make policy and make rules that are consistent with reducing congestion. There's no magic wand here. There's not one policy that could lead to results. It's probably, if I had to summarize it based upon our findings, it's a combination of a lot of different policies that have to work together. And we put this framework together. It's a proposed framework. It's not finalized yet. We have a draft report, which if you contact me, I will send it to you. We started with a workshop, which was held at our virtual conference last December. You know, we had experts in congestion mitigation, including London's TfL, which presented on how the congestion pricing scheme in London had evolved over the years. And we received comments from the attendees at the conference, and we consolidated them, and now we're having one final panel at our Memphis conference in September, and then we'll be issuing our final report. So here's the principles. We'll run through them. I think the 5 root causes of traffic are private car dependence, modal shift from public transit, for-hire vehicle growth, surging e-commerce, and ineffective policies. You know, the first one is congestion pricing, you know, road pricing. The first principle is that the use of congestion pricing should provide incentives for sustainability and equity goals. You know, one of the things that we threw out there is that we should have a meaningful policy directed towards a lockbox or a designated revenue stream, which instead of throwing new money at old bad policies and fixing trains and providing you know, the same old service, we should be looking at the ecosystem. Let's use some of that money for you know, first and last mile partnerships or mobility as a service. You know, right now the MTA, the public transit agency in New York, has been is under a mandate to put together a congestion pricing scheme. And
because it's on the.
I'm sorry. There is a panel that was just appointed to come up with exemptions, and too many carve-outs don't make sense according to our guiding principles. Some may. Right now we have emergency vehicles and people with disabilities, but we think that this board and anyone who adopts in the U.S. Congestion pricing should look at maybe exempting shared rides or exempting electric vehicles, providing incentives to make the air cleaner. Number 2, multimodal integration should be here. It's not everywhere. Mobility as a service, public-private partnerships, mobility hubs. This is part of our congestion mitigation strategy, and we should be doing more of it. We've only had these FTA projects with on-demand services that have been experimenting, but we need to go to the next level. There's some great stuff going on in Houston with the Connect Smart program, which is already doing a mobility as a service system, which is partially federally funded. And I would urge you to take a look at that ecosystem that they're putting together there. And there are other cities experimenting with it. And in our view, we should go further and do more. Maximize vehicle utilization. We need to identify business and regulatory solutions to increase vehicle utilization and efficiency. One example would be mixing passenger and goods delivery. There are companies now, and Uber Eats is a good example, right? But there's also package delivery going on in between passenger trips. Every vehicle on the road should be used for something if it's going to be on the road, in our view, you know, every second of the day. There should not be deadheading, downtime. Principle number 4, deploy innovative goal-oriented street design principles. Explore the use of private property and off-street parking facilities to stage vehicles. Get them off the street when they're waiting to pick up their passengers. Review curb space policies to encourage expeditious pickup and drop-off of goods. Provide incentives for clean air vehicles and dedicate parking spaces for car sharing. Many cities are already doing this. We need more. Item 5, implement sustainable transportation incentives and disincentives. You know, the use of HOV and bus lanes, preferred curb space access and subsidies, you know, providing disincentives to personal vehicle usage, you know, using the bus lanes potentially for, you know, shared taxis, right? I mean, why not? Thoughtfully plan to improve and expand EV infrastructure. Upgrade and expand the infrastructure so public transit services are real options for everyone. One of the key points we want to make here is that you know, a master plan should be developed by cities, and EV infrastructure needs to be a part of it. If you let the private sector just put EV infrastructure where they feel like it, Nobody benefits, especially if they're public charging stations. You could have a cluster of charging stations that are in inaccessible areas of the cities. So a master plan should include EV infrastructure and plot it out ahead of time, not after the fact. There are 10 principles, by the way, so we're almost there. Item 7, promote shared mobility wherever you can. During the pandemic, some cities had discouraged or even banned, like New York City did, sharing rides. Now it's back, and it appears that we're starting to share again. But this is something that helps to improve environmental outcomes. It's not the answer to everything, but it's a factor. Not just pooled rides, to mitigate congestion, but shared mobility in general. Using micro mobility and micro transit. Item 8, this the civil rights issue of our time is accessibility. We don't have proper accessible service. We need to fix this problem. Uniform systems of service delivery and subsidized public paratransit need to be everywhere. The system's broken. There are great experiments going on in different cities, but there should be point-to-point transportation using wheelchair vehicles and smaller vehicles rather than grouping people together on inefficient routes, which has led to the waste of hundreds of millions of taxpayer dollars since the ADA was put into place. 9, always promote equity in your decision making. Exemptions for low-income individuals from congestion pricing. Always look at how people who cannot afford or unbanked communities can't afford transit are impacted by our policies. And last but not least, item 10, this is a big issue for many, reducing the size of government fleets, getting rid of unnecessary parking placards for privileged managers who don't really need to have them in the cities. Explore using taxi cabs, TNCs, and for-hire vehicles instead of buying more government vehicles. This is something that is already being done at the federal government level. There's an $810 million contract so that federal employees could use Uber and Lyft to get around instead of buying cars. And cities everywhere should be looking at optimizing their fleet. In New York City, we have a municipal fleet share, almost like a zip car for city vehicles, so that we use them efficiently and effectively, and someone's always sharing one. Or frankly, replicate the GSA model in cities and states so that the city and state vehicles can reduce their fleets. So I think I'm just at about 12 minutes. We're looking for comments and thoughts. This is not a final project just yet. We are probably going to issue the report sometime at the end of this year or early next, and we hope people will look at it for their research, the next research projects, or to policy. And if you send us an email at info@itr.global, we'd be happy to get your thoughts and comments. And you have any research that is relevant to these principles that you'd like to share with us, we'd be more than happy to incorporate it into our final report, which will be read by transportation policymakers around the world. So I want to thank you for your time and for accepting my abstract. And it was great to be here. And I'm happy to answer any questions, Krishnan.
Thank you so much, Matt. Anybody from the audience, you have any questions? So there is a question from Yushoy. Hold on, let me just read that. For the congestion pricing in New York City, I'm wondering if there are any direct support to alleviate emissions. I remember the plans to support public transit systems.
Well, yeah, that's a good question. It's not, it's amazing how we're not talking about eliminating emissions. This is all about grabbing money from the public to help the MTA. The problem that we have in New York is that the COVID money that came, the COVID relief money, is running out. People are not using the subways and they're fearful of using it. So the MTA has a fiscal crisis once again that they're facing. And there's been no talk about that. There's been no talk of using this money for innovative partnerships, emissions reduction. It's really just the money grab. And I think that needs to change. And I hope the dialogue changes. And remember, I just want to remind everybody, the MTA has already been collecting a congestion charge from Uber and Lyft and taxi cabs for the last 4 years. Almost $1 billion was paid into the MTA. And, I just think they're using the money for budget shortfalls, but I think we need to maybe focus on alleviating emissions and having a portion of that money be dedicated to maybe a clean EV mobility hub, right? Why shouldn't there be one in a transportation desert at the last mile, as opposed to putting more buses that aren't used in 2 or 3 fare zones? So it's a good question. I hope the debate changes on this. It's coming. I think it's going to happen eventually, but we'll see how it plays out.
Anybody else has any questions? If not, I have 2 questions. One is, you mentioned TNCs and using it. The question is in terms of getting data, because I work with the public sector, and for us, the biggest hole on the passenger side is getting visibility into the TNC movements. I mean, Uber did some program, but it's at a very aggregate level. I know that LADOT came up with the mobility data specification. And is that going to be adopted as part of your this guidance that you're putting out later this year? And then the second, sorry, go ahead.
That is going to be part of our guidance in terms of using the data. Lacuna, I actually did work on the mobility data specification for LADOT as a consultant, and Lacuna is coming to our conference, and they're going to be talking about what they did in LADOT, because it's gone beyond just bikes and scooters. And I know this is a big issue. As a researcher up at CUNY, for years we've been pushing for open data platforms, and some of the companies have resisted. In fact, I think all of the companies pushed back against the TLC when they started. I collected the first set of data when I was there for taxis, but then after I left, the TLC got Uber and Lyft data, but they pushed back saying we can only do it based upon zip code. They were concerned about sharing proprietary information. But a lot of cities, not LA, Chicago, TLC, we have robust data sets now, and it's better than not having the data. But I believe there should be more, and companies that are putting together these open data platforms do a tremendous service to the community and to the research community. And we've been, I've partnered with UC Berkeley and Susan Shaheen, and we've been for the last 5 to 6 years doing hackathons in our data commons where we get public and private data. But since then, we've seen a lot of different cities push these open data platforms, and more needs to be done. And the data is very, very important for researchers like yourselves to come up with policy, and that is going to be part of our final report, what regulators should be doing in terms of obtaining the data and making it available so that we can make good policy.
And just an observation for your government fleets, I saw no mention of transit or biking, only taxis and TNC. So maybe, I don't know. I don't know what message that's sending across. So you might want to.
Well, no, we're fans of it, but it doesn't solve all of the problems. It's one of the things we can do. But I think honestly, there's been an overemphasis in local DOT circles universally across the globe and the US on this being the answer to everything. It's not. Disabled passengers cannot take scooters and bikes.
I agree. Yeah.
It doesn't work in cities like the city of New York as compared to the West Coast because of weather conditions. But yes, it's one of the tools in the toolbox. And we have a cap on the number of FHVs in New York now too, and I don't think that's going to be lifted. But all these different things working together help, but not one is a solution. And congestion pricing is not a solution either. That's one of many different things that we could do. And for researchers, I think we should bear in mind like the ultimate policies that these people are making when we're doing the research. And some of the research I've seen so far in the conference is great, Krishnan, and I'm looking forward to the rest of the presentations.
All right. Thanks, Matt. With that, we'll move on to our third presentation. Our third presenter is Matt Bruchon, and he's a postdoctoral researcher in the vehicle electrification group at Carnegie Mellon, where he completed a PhD in engineering and public policy. Matt investigates the environmental and social impacts of transportation and related policies using optimization, econometrics, and machine learning. Prior to this, he completed a master's degree from MIT in technology and policy and electrical engineering and computer science, and worked as a machine learning consultant for government and industry clients. Matt's going to present some findings on the emissions that result from electric vehicles in the mid-eastern region of the United States. Take it away, Matt.
Thanks, Krishnan. I appreciate the intro. So we're going to switch gears a little bit now and talk about electric vehicles. The study that I'll talk about today is co-authored along with Lance Chin and Jeremy Michalek, who is the corresponding author, all at Carnegie Mellon.
Can you speak up a little bit? You come across very faint. So
sure, yeah. I'll speak up a little. I'll move my mic a little closer too. Is this any better?
Yeah, that's better.
Okay, good. So the underlying question that motivates this study is what power plant fuels your electric vehicle? So it's well established that plug-in electric vehicles can mitigate climate change and also reduce health damages that come from air pollution when they're charged from clean power sources. But if PEVs are charged with coal-generated power, for example, they can have higher greenhouse gas emissions and also higher criteria air pollutants, things like particulate matter, than we would see from gasoline vehicles. And there's a large body of literature that produced those estimates and that documents some of those findings. So what we know is that PEV emissions depend heavily on regional factors, and simulation can help us estimate them. And so the underlying issue here is not only whether or not we have renewables on the grid, but also which power plant is actually operating on the margin, where if I start to charge my EV and there's a little extra load added to the grid, there's a specific power plant that might need to ramp up in order to meet that load. And so that's what we're looking at in this study, is the specific consequences of shifting vehicles to electric and their charging loads. Specifically, I'll talk about the PJM Interconnect, Pennsylvania, Jersey, Maryland. It's the country's largest regional transmission operator. You can see the map on the left hand of the slide here shows that service area. And it's historically been relatively coal heavy, but it's been evolving rapidly. So the right hand table you can see here shows the generation changes since 2010. Natural gas plants did increase. This was mostly relatively efficient combined cycle plants. And coal power also went down by about 15%, I believe. We've also, in addition to those changes, seen a relatively drastic increase in renewable use, at least in percentage terms. So changes are underway in PJM. There was a 2016 study which used 2010 grid data. It was looking at PJM also, and this study found that as of 2010, plug-in electric vehicle emissions could be substantially higher than internal combustion engine vehicles. The plot that you see here is from that study, and to be more specific, they found that battery electric vehicles could have 2 to 3 times higher consequential emissions externalities than internal combustion. And when I say consequential emissions, I'm referring specifically to that directly induced new emissions from switching to a battery vehicle. This includes things like battery manufacturing, but it also includes changes to the way the power grid operates. So another estimation of that study was that as PJM saw more coal plants retire, plug-in electric vehicle emissions should fall, and perhaps the trade-offs between plug-ins and ICE could change. So what we've done for this study is essentially reuse the model from this 2016 paper, but with the most recent possible data for the power grid. And so the optimization that we're running is a power grid optimization. The objective is to minimize total operational costs. The inputs are, on the one hand, grid side, things like the non-charging demand, so all of the status quo things like lighting, heating, cooling, that all go into the power grid. We also look at the historical renewable output from wind and solar. And we have a series of variables to characterize each power plant that's in PJM. The constraints are, first of all, that supply from the grid must equal demand. And that demand also does include electric vehicle charging. in some cases. And so what we get from this model that's requiring that supply be met and also modeling individual generators and how they operate, what we get from this is each generator's output, both in terms of megawatts, but also in terms of the emissions that these power plants produce at each hour. We take these grid operational emissions and we combine them together with a life cycle analysis. So our first set of findings looks at the year 2019. This is the most recent year that we have all of the data sources that we need for. And what we see for 2019 is that plug-in hybrids and battery electric hybrids both are more or less on par with hybrids and internal combustion vehicles. So what we label in the rest of these slides as PHEV, this is a plug-in hybrid electric vehicle with a range of 20 miles. And BEV 300, that's a battery electric vehicle with a range of 300 miles all electric. And so the BEV, you'll notice the pink portion of the bar here is relatively large. This bar chart is showing across the full lifespan of an average car, the total external costs, or essentially the climate change and health damage impacts that result from that vehicle. So for an internal combustion vehicle, for example, that number is around 7,500 per car. For battery electrics, that number is just a little bit above 7,500. So at first glance, this might look like bad news in terms of the potential emissions impacts of plug-in vehicles. But if we compare this to that 2016 paper with 2010 grid data, it's actually quite a substantial drop, both for plug-in hybrids as well as battery electrics. So the next question we looked at is why, or how I should say, how the grid dispatch changes when you add this load from electric vehicles. The largest change is that when electric vehicles are charging, more combined cycle natural gas plants are used. There's also a smaller increase in coal plant use, as well as other forms of natural gas that are a bit less efficient. You'll notice one thing missing from this plot is wind and solar. That's because in PJM, wind and solar are generally not the marginal generator that's going to be curtailed or increased when load changes just a little bit. Next, we looked at the year 2025 because we know there will be additional retirements for certain power plants, as well as some new installation of renewables and other things like natural gas. What we see for 2025 is that, again, plug-in hybrids and battery electrics both continue to fall in terms of their life cycle emissions, but they're still more or less on the same order of magnitude that we see for internal combustion and for hybrids. And again, a big reason for this is not only those consequential grid emissions, but also that pink portion of the bar that you see for battery electrics, which represents battery production emissions. One thing we were curious about was what would have to change in order for battery electrics to either have much lower or perhaps much higher consequential emissions. So this plot is showing as the purple and orange lines, internal combustion and hybrid vehicles. And the kind of teal line here is a battery electric car. And so what we see projecting out to 2035, in our base case assumption, we see that battery electrics are pretty close, once again, to internal combustion vehicles. One thing that turns out to make a huge difference is the battery chemistry of that lithium-ion battery. So if we were to switch, for example, from a nickel manganese cobalt battery to a lithium iron phosphate battery, those are the two lower test cases that you see down near the 5,000 range. And with that LFP chemistry, the emissions from a battery vehicle are substantially lower. On the flip side, if battery chemistry were to switch to an even more nickel-heavy chemistry, we would see those consequential emissions raised for battery electric vehicles. So chemistry is important. Next, we looked at plug-in hybrids. This is the same style of plot, but that pink line is plug-in hybrids. And what you see here, the trends are pretty similar. Battery chemistry is very important. Other variables also make a difference. But overall, the range of uncertainties across our test cases is much smaller for plug-in hybrids. So a few takeaways that I would highlight. One is that across all of the future cases that we tested for the power grid, through the year 2035, we anticipate that the consequential emissions from PEV charging will remain substantial to some small or large extent. We also saw that pretty consistently the single largest source of emissions costs for plug-in electrics is from nickel mining, and that's specifically sulfur dioxide that gets emitted when you produce nickel for nickel manganese cobalt batteries. This sulfur dioxide, it has a pretty drastic impact on health damages, which are a big portion of those bar charts that you saw. However, it doesn't drastically raise climate change impacts. So across most of our scenarios, battery electrics still are on par or a little bit cleaner than the next cleanest powertrain. And we also, just to reiterate, saw that alternative chemistries like lithium iron phosphate can drastically lower externalities. And a final point that I would make is that another way that we could reduce these life cycle emissions for battery vehicles is by right-sizing the cars and the trucks that we use, making them smaller for use cases where that works, and potentially also right-sizing the batteries that these cars have. So with that, I'm happy to take any questions. Thanks.
Thanks, Matt. Anybody have any questions? So the one question I have is, your basic takeaway is having a lithium phosphate ferrous iron battery is a better option, right, from an emissions. But in your estimation, I think you looked at everything from the grid side, but on the vehicle usage side, the emissions that an ICE vehicle is emitting versus what EVs emitting. Won't that be good in your estimate and your optimization? Or you just, because your problem is focused on the electric grid and its impacts on the external costs?
Yeah, so what we do for the final analysis, like what you see in this bar chart, is combine together the grid emissions as well as the tailpipe emissions. So in this particular plot, that's the orange bar. And you can see that it is, that's a very large chunk of the costs for internal combustion. That's almost all tailpipe, greenhouse gases, and particulate matter. And so that is still a substantial piece of the equation here.
Okay. But I'm guessing these other things can be made narrower, right? If you change the battery chemistry, as you pointed out, and also the source of electricity, both those can help with making the costs lower than ICEs.
Certainly. The battery production is kind of the single, perhaps lowest hanging fruit, you might argue. Alternative chemistries might turn out to be more economically efficient anyway. So it's possible we'll see those things change. We did also run a bunch of test cases on the grid side, looking at things like accelerated coal retirement and things like, additional wind and solar. And we're still analyzing those findings, but one consistent finding is that if you retire coal plants faster and replace some of that missing capacity with combined cycle natural gas, that can also improve outcomes.
Right. That's great. Thank you. Anybody else have any questions for Matt? Thank you very much, Matt.
Thanks.
Our next speaker is Hossein Gazmeh, and he's a first-year PhD student in transportation engineering at the University of Alabama. He received his BSc in Industrial Engineering from Amir Karib University of Technology, Tehran, Iran. And his primary interests of research, primary areas of research are urban mobility, transportation networks optimization, and EV infrastructure. And today he's going to talk about the national level disruption due to the pandemic and investigate if structural disparity existed that disproportionately affected the access to transit for people from different racial groups. Go ahead, Hossein.
Okay, I'm excited to share with you my recent research on the structural racial disparity as a result of COVID-19 transportation access and supply. So let's just get to it. So first, I want to mention, as we all know, COVID-19 had a major impact on every aspect of households' well-being all across the country. But still, we saw, and there is a growing body of research that capture there is a disparity between different communities in whether in social or economic inequalities that they suffered from. Also, on the other hand, we know the essential role of public transportation for communities of color and the more disadvantaged communities, whether it's in access to critical services or any other daily basis needs that they have. So combining these two and reminding ourselves that transportation itself has been from a long time a core of discriminatory policies. We are now interested to see how transit systems and agencies are operating, and are there any racial disparity between communities of color or not across the country as a result of COVID-19. So more specific, we are trying to answer first, is different communities or different racial groups are suffering differently? And second, if we consider the initial level of service that they are receiving or the pre-pandemic level of service, does the disparity remains the case or not? And third, and most important, we want to see if that disparity is systematic, meaning it's happening across the country from different agencies with different capabilities or not. Now, what we do is basically we gather the data from transit agencies pre and post-pandemic. Pre-pandemic, the closest date to basically late 2019, and also post-pandemic from mid-March to early July, the first wave. And we want to capture, we gather the data from the operational perspective, their transit stops, routes, trips, etc., from the GTFS format that they are reporting. Also, we matched that to the entity profiles of those transit agencies. We want to see what is the other characteristics of those agencies. Also, we want to see who are the people that are affected. So we look at the census tracts that are being covered by these agencies. What is their social and demographical and socioeconomic features? So basically, we want to see who are the ones that are impacted by agencies and how the change will, basically varies across the community before and post-pandemic. But we gathered these after all the processing, 111 transit agencies from 44 different states, and basically covering more than 77 million Americans and more than 19,000 census tracts. So regarding our first question, we can clearly see from the initial looking into the data, we can see there is actually a very visible trend that more disadvantaged communities are being hurt the most. So as you can see, there is a clear, consistently attribution from higher income people that are receiving less or no change. And also that is the case for no vehicle or transit dependent people. So basically, the ones who need it the most are being affected the most. Also, if you look at the racial composition of such communities, we can see that there is a very opposite trend for Black and white population, something that we will see all across the other, like our next results analysis. But for Asian Hispanic, still no communities that had more than 15% Asian or 35% Hispanic had undergo no change. Basically, they all had mid-low to high levels of change. And for Black population, any communities with over 50% Black population had gone under the severe, significant reduction into their level of transit system. Now, so we can see basically there is, the first glance, there is a disparity between racial groups, as we talked about. But we have to argue and look into the immediate effect of their initial level of service that they are receiving. So if a community is receiving a higher level of trips or service by the agencies, it is expected for them to have a higher rate of change. So what we do here is basically accounting for that through a causal mediation framework. As you can see here, the reason we didn't go through like more traditional frameworks such as SEM or etc. was because of the dependency of X to M and M to Y paths. So also, so basically what we want to get from such a framework is to see if the effect of race on change rate is from basically their level of initial trips at 2019, or is a direct effect and attribution of race on the change rate. Also, we had another confounders to check, like agency scale and transit dependency, to see how they are attributed and what is their influence on trips 19 and change. But since I'm trying to basically capture all of my results more into the 12 minutes, we're gonna basically pass that. So, but our second question basically was, if we account for the mediation now, if the results remain the same or significant or not. Now, it's actually quite interesting because from the Black population, if you look, most of the reason that they are being hurt the most is because of their much higher level of transit dependency. So it's through the ACME or the mediation that we talked about. So since they had a much higher level of trips, that's why they went under such a significant reduction. However, the effect of direct effect is basically negative, meaning that agencies have tried significantly, at least in part, to basically account for the reduction or eliminate the reduction as much as possible for such communities. The results are, as we talked about, completely opposite kind of for white people, where the attribution to the less transit, to less reduction is because of their less dependency of trips before the pandemic. However, their positive direct effect is not significant. But what we see here for Hispanic and Asians is not only they are being ignored for their initial level of service, but also they are subject to significant change in their transit, which basically can account for disparity in their reduction, as we talked about, compared to the other racial groups here. Now, so we saw already that there was a disparity which remained between racial groups, even if we accounted for the mediation of basically their initial level of service. But now we want to see if it's systematic or not. So for that, we can go through the agencies and see what is their direct, indirect effect on, basically based on race, how they are treating different races, so to speak, based on their response to the pandemic and the change reduction we observed earlier. So if we look at the causal mediation effect across the agencies, we see basically for the Black people is over 60% significantly are trying to, they are basically considering their initial needs, and that's why they are receiving such a high level of trips. So we can say basically for Black communities, there is a systematic acknowledgement of their needs, where they're not only receiving a much higher level of trips before the pandemic, but after the pandemic, and as we can see in the next slide, they are actually trying to stop the reduction as much as possible. So they are negatively basically influencing the change reduction, more change reduction. For white people is the opposite, as we talk about later, but for Asian and Hispanic, we can see significantly there is no indirect or causal mediation effect, which accounts for their neglection of their needs, basically. Also, if we look at the direct effect, we can see, for example, for Black communities, that direct effect is for all agencies is negative, but for more than 30% being significantly. So they are significantly trying to reduce the reduction for such communities. However, for white communities, although they don't have much of a dependency, they are the ones who basically do not need the transit as much. We can see only a proportion of agencies that are trying to actively reduce their transit trips. However, for the Asian and Hispanic, similar to the previous slide, these communities, but they are subject to the post-pandemic reduction in the transit system. So, just as a summary and conclusion, we can say for Black population is still, although there was a systematic effort to answer their transit needs, they are the ones that are being hit the most, as we saw earlier. But for white population, still they remain the least impacted because of how much they were less dependent on transit. And although the agencies did not effectively try to reduce the transit level for those communities, however, for Hispanic and Asian, we can say there is a substantial structural disparity, where they're not only being ignored at the initial stage, but they are subject to systematic neglection after the pandemic in the reduction of service. So, thank you very much. I'm open to answer any questions you might have.
Thanks, Hossein. Anybody have any questions? I have one quick question. Is this consistent across the country, or you notice some?
Yes, it is consistent. And so basically, I try to jump much of the methodology that we talked about, but the agency's scale, different capabilities are being accounted into the multi-level causal mediation framework. So we can basically, we are accounting the different capabilities of agencies from different sizes all across the country.
And then there was a question in the chat. I was wondering, how did you measure the trips for different places?
So what we did for measuring the trips is basically we gathered the GTFS data for the transit agencies. So we know the geometry of the trips, the routes, the stops, etc. Also, we know where are the census tracts located by the data provided by Census Bureau, etc., and their socio-economic or demographical status. Then we can see which route is corresponded to which census tract and how we can basically capture the number of trips that each census tract is being accounted for by agencies.
Thanks, Hossein.
Okay.
All right.
Thank you.
Anybody else? Any questions? If not, thank you for your presentation, Hossein.
Thank you.
We move on to our next presenter. Our next presenter is Bingrong's son. Bingrong is a researcher at the National Renewable Energy Lab. Her research mainly focuses on traveler behavior analysis, travel demand modeling, and ITS, particularly investigating the interactions between travel behavior and emerging transportation concepts and leveraging ITS technologies to improve both transportation system performance and traveler benefits. She's also interested in exploring the interdisciplinary research topics between transportation and other domains, such as building technologies and power systems. Today, she's going to talk about demographics microsimulator, which is powered by the world's largest running panel data survey, which can capture a host of life cycle events to inform transportation planning and policy evaluation with population dynamics. So take it away.
Thank you for the introduction. Does everyone hear me well and see my screen?
Yes, thank you.
Okay, that's great. Hello, everyone. I'm very happy to be here to share of some of our recent research effort. It's called Demographic Microsimulator for Integrated Urban Systems, Adapting Panel Survey of Income Dynamics to Capture the Continuum of Life. And I believe my co-author Juan and maybe Ming or they are joining me as well today. So if you have any questions, please feel free to drop them in the chat and they will be helping me to answer the questions. Okay, so we can start with the research motivation. We know that travel demand forecasting is one important component in many of applications like transportation planning or something we discussed earlier today, like EV charging demand, congestion pricing, or even the transit system planning. And these kind of models often rely on cross-sectional or slice in time of synthetic population information, which basically means if we want to do the travel demand forecasting for a particular future year, we will take the population and its composition for that particular future year to do the travel demand forecasting. But researchers already found that life cycle events, its timing and the sequence have significant impact on people's travel related decisions. Example here could be like a new baby, having a new baby is going to have impact on people's car acquisition decision or vehicle usage pattern. Some existing effort has been trying to address this, trying to inform the travel demand forecasting with this timing and the sequence of life cycle events by modeling how the population evolves over time so they can provide the population dynamics to inform the travel demand forecasting. But these existing efforts still have some limitations. Some of them are developed from cross-sectional data in which the data itself does not really reflect the sequence of life cycle events. And the one or two that are based on panel data set, they do not really cover all the important demographic events that are influencing people's travel related decisions. But meanwhile, there is a very valuable panel data set out there. It's called Panel Study of Income Dynamics that covers a wide range of life cycle events. I'm gonna talk about it in details later, but it is the world's longest panel data set that can provide really valuable information to inform the population evolution modeling. So given the existing limitation and the valuable data source out there, we proposed this demographic microsimulator demos. It can capture the interdependency between short-term and long-term life cycle events. So how does this demo work? The framework on the right-hand side kind of showed the modeling flow of these demos. It starts with the synthetic population for time t. And then all the individuals and household inside of synthetic population will go through the three major modules inside of demos. The first module is a migration module. All the household inside of the synthetic population will determine like if they want to keep staying in the study region or if they want to move out. And also if there are some new household who want to move inside into the study region. So after this step, we will have all the individuals and household that will stay in the study region, and they will go to a next two major module. The first one is individual level evolution. That consists of a set of submodels such as mortality, getting married, education enrollment, and a grown up child leaving their parental home. And all the household will go through the household level evolution. That is another set of submodels, including cohabitation, divorce, newborn, income, and relocation. So after the individuals and household go through these three major modules, their demographic characteristics will be updated, and that will form the synthetic population for time t+1. And then it depends how many years we are interested in to simulate. We can iterate this process to generate the population dynamics for that many years. Just to give you a better idea about how different submodels or life cycle events are working together inside of demos. Here, the figure on the left-hand side shows that all the life cycle events are integrated into a sequential simulation process. So it should be noted that the sequence of these submodules itself is a parameter that need to be calibrated, to be investigated, to see like which sequence can better represent the population dynamics in the real world. And then to give just more details on different life cycle events, the blocks on the right-hand side, those are examples of the life cycle events models inside of demos. Take the first one as example. It is a mortality model block. So a person that is currently alive will go through the mortality model, and the model will tell if this person is gonna stay alive or has a mortality event in the next simulation year. And similarly, we in the family restructuring model on the right-hand side, if a person currently is a single status, and then it will go through the single to X model, submodel. And then the model will tell if this person will keep staying single or start cohabitation or get married in the next simulation year. Other family restructuring models, things like if the person's status is in cohabitation or is in married situation, then what would be the outcome of their status in the next simulation year? So all these submodels or life event models are in either in binary or in multinomial logic format, and they are applied to the eligible populations. So once we have all the framework and the model structure defined, we actually used the panel study of income dynamics, PSID, the data set I mentioned at the beginning, to inform the estimation of those submodels, to give those life cycle events model some behavior logic. And this is a data set, this is a world longest running nationally representative longitudinal survey. The survey started collecting data from 1968, and it is still running in current days. It collects information from participants, from their families, from their descendants for their whole life, as long as they are still willing to stay in the survey, about their socioeconomics, demographic, health, and attitudinal characteristic. So that's a really rich data set out there to inform the demographic modeling. We use the public available family and individual level data set in PSID, and we used the most recent 20 years data to inform the model estimation. We processed the raw PSID wave to wave, tried to identify the important demographic events. Example of those demographic events are like a example shown in the previous slide. And before we really use the data to model the subset of the submodels, we kind of compared the demographic trends identified in the PSID versus the CDC observed demographic trends. On the right-hand side, you can see that the mortality, birth and fertility, and the marriage rate The trend identified in PSID have a good representation as the real world trend. So that kind of confirmed that the PSID is a valuable and a good data set to do this demographic modeling. So we have the model structure defined, we have the data ready, and then we went ahead to estimate all the submodules inside of Daus framework. And these each submodel describe one life cycle event, and the dependent variable is a life cycle event, and the explanatory variables are the socioeconomics and the demographic features. So all these models are behaviorally intuitive, and we have some kind of interesting behavior implication found from these models. For example, take the mortality model as an example. Females, in our model, we observe that females have a lesser likelihood of mortality, which is consistent with current like a health or social science study. So other models are also having some interesting behavior implications. So after we have all the framework established, we have the model estimated, we tested the performance of demos in San Francisco Bay Area at the case study. We simulated the regional population dynamics between 2010 to 2019. And then starting with the synthetic population for 2010 and then generated from population sim. And then we put that synthetic population as input into the demos and then progress them through the whole framework on Urban Sim platform. So this platform allows us to more efficiently simulate all the submodules and also their interactions among them. So we iterate the demos framework year by year between 2010 to 2019, and we generate the population dynamics for each year. And then we kind of compared the predicted population trends versus the observed population trends, the data that we found from California Department of Finance, to see like how demos performance is. And it should be noted that we also incorporate some calibration effort here, that including like trying to calibrate the intercept of the submodels inside the demos. And also, as I mentioned earlier, the sequence of the modules also matters. So we tried a different sequence to see which one can better reflect the population dynamics in the real world. So after these efforts, here are the results of how demos work, how demo works. Here are 4 major demographic trends. The first one is population, and then the number of household, number of birth events, and the number of mortality events. The simulation one is in the orange bar, and the observed one are in blue bars. As we can see that demos result has a reasonably well representation of the real world population trends. So it comes to the conclusion. This research proposed a demographic microsimulator that is powered by the world's longest running panel data survey. It can capture a host of life cycle events as well as the interdependency among these life events. And the output from demos can be used to inform transportation planning and policy evaluation with population dynamics. And all the demos life cycle event models have statistically significant parameters and show behaviorally intuitive trends. And in the case study of San Francisco Bay Area, demos also shows reasonably good representation of real world population trend. And we also observe that demos is reactive to the interconnections between various life cycle events. So in the future, we're planning to improve the performance of demos by improving the performance of some submodels, investigating the impact of model sequencing on the performance, and also perform the case study in other regions to see if the demos performance is consistent. So here's, that's all what I have, and your questions and comments are welcome.
Anybody have any questions for Bingrong? Just have a quick question. What is the specification for your mortality model?
Yes, the mortality model has something like age category, age things, and then the gender, employment status, and education status, and also some marital status. So those are the significant variables inside of mortality. Some interesting fun fact to share here is that when we use a little older data set, like earlier, starting like 1968 or 1970-ish, like here's a kind of result. And we also found like a race is also kind of significant in the model. But after we start to use like more recent years data, the race variable is become insignificant. So I guess that's a good thing. Yeah.
One more time for one more question, Ronak.
Yeah, hi. Thanks for your presentation. Really quick question. So you mentioned that you were using 20 years worth of data, right? And just wanted to clarify whether the models that you're estimating are static or dynamic.
Currently, it is static, but we are thinking like to consider some lag variable to incorporate some kind of dynamic features inside a population evolving trend. But the current version is static.
I see. So it's kind of like, because this panel data, so you pool 20 years worth of observations and then estimate static models on them. Is that correct?
Yes, that's correct.
Okay, great. Thanks.
Thanks, Bingrong. And with that, we have like half an hour left and 3 more presentations to go through. Our next presenter is Emma Luccan. Emma is a PhD candidate in transportation engineering at Cal Berkeley. Her dissertation focuses on the equity, accessibility, and environmental impacts of public microtransit services. She has received a National Science Foundation Graduate Research Fellowship and 3 Eisenhower Fellowships. Emma has worked for the Volpe National Transportation System Center, the Minnesota Department of Transportation, and Twin Cities Metro Transit. She currently lives in Minneapolis with her husband and 3 young children. And her presentation introduces the use of shared error components in a mixed logit model to explore correlations between public microtransit and more established modes such as bus, driving alone, and Uber and Lyft. So with that, Emma, the floor is all yours.
Great, thank you very much. Okay, and I'll try and be quick to catch up on some time. Okay, here I think, darn. Let's see, I just have to change the settings so that you guys don't see that. There we go. Okay, so yeah, my dissertation looks at public microtransit services, which are on-demand services in van-sized vehicles using an app, ride matching, and routing algorithms. And today I'll be talking about some methods that we've been looking into to estimate a little more complicated variance-covariance matrix to start to capture the correlation between this public microtransit mode and Uber and Lyft modes, drive alone, and bus modes. So I just sort of define that quickly. And like I said, I'll try and run through this quickly. So just mentioning that this is even before the pandemic, there were 62 different public microtransit services across the country, and it's only increased during COVID. Our main focus or questions are, what are the DMT, accessibility, equity impacts of these services, and then how can agencies optimize the impacts of the services in different pandemic and post-pandemic scenarios in their service designs. So we developed a mode choice model from a stated preference survey of over 1,800 people across 14 agencies with these types of services. About two-thirds of those were frequent users, 300 infrequent, and 300 people who had not used the service before. And each person answered multiple pre-pandemic scenarios and pandemic scenarios. And there's 7 modes in the model. So there's this microtransit mode, there's a ride alone Uber, shared Uber, a drive alone, fixed route bus, and then 2 first mile, last mile modes, with the microtransit as the access mode, and then the Uber and Lyft as the access mode. And so the focus of this presentation, so we wanted to use the model to, we wanted to apply the model to microtransit trip data. We have over 400,000 trips from 8 agencies over a year and a half. And we wanted to apply the model to those trips to estimate replaced modes and calculate impacts. However, the variance covariance matrix plays a big role in determining the substitution between microtransit and other modes when forecasting impacts and estimating the replaced modes. And so usually you would choose between, a restricted diagonal matrix, but that could ignore correlations between the public microtransit and the other modes. And then for a full covariance matrix, you can't, if I'm focusing on the correlation between the 7 modes, I can't estimate a full 7 by 7. I would have to just estimate variance covariance matrix of the differences, because you have to set 1 to 0. And so then the interpretation is more difficult. So our approach is to use a mixed logit model with shared error components between the modes, and test different hypotheses around the which modes are correlated, and see which combination yields the model with the best log likelihood. So here's just a representation of that with the 7 different utility equations. Here I just have the error components in there. So these are the equations below. You can see those are the ones that ended up being significant. So you can see like the 3 on-demand modes, the public microtransit, as well as the ride-along Uber and the shared Uber, they have that error on demand as one example. And then after you estimate the model, this is how this is the results that it spits out. So each of these different error components are significant. And then once we have these values, we can estimate a correlation matrix between the modes. And so here, obviously, along the diagonal, you have ones. The dashes are the showing where there's not correlation, or that the correlation between those modes did not come out as significant. What you can see with the coloration here, the color scheme, the respondents to the survey, at least from their perceptions, the Uber and Lyft modes are the most highly correlated. And then the bus modes, the 3 modes that include fixed route bus, are next most correlated. If you just look at the top row, that's the correlation between the public microtransit and the other modes. And so interestingly, the people who took the survey, and maybe because they are frequent microtransit users or users of this new public mode, and they might see it as a substitution for drive alone. So that the highest correlation is between microtransit and drive alone, and then the next highest is with that first mile, last mile mode, where microtransit is used as a feeder to bus, then bus, and then least correlation between the Uber and Lyft and pooled modes. And so to sort of explore whether that hypothesis was correct about it being influenced by the frequency of times that the people had used microtransit. This is split across, the top is the most frequent microtransit users who have used it more than twice. The middle is people who have used it only once or twice, and the bottom is people who have never used microtransit. And so we re-estimated the model with these error components for each of those groups. And as you can see, as microtransit use increases, so going from bottom to top, the perceived correlation between microtransit and drive alone actually decreases, and the perceived correlation between microtransit and bus also decreases, and also the perceived correlation between the 3 Uber and Lyft modes decreases. But conversely, for people who have never used microtransit before, they do not perceive any correlation, or their perceived correlation between microtransit and the Uber and Lyft modes is insignificant. So they don't perceive a correlation between those, whereas people who have experienced the mode do perceive those as being correlated. So that could indicate something positive, that the service has succeeded for people who have actually used it. They perceive the benefits of it to somewhat approximate those private versions of that mode. So the next steps are to continue comparing correlation matrices across other demographic variables, such as the significant demographic variables in the model are income, age, access to personal vehicle, and smartphone ownership. And then also to apply the model to those microtransit trips that I mentioned, using this model to inform what modes would people have used if microtransit was not available. And then we can adjust the variables in the model, the service design variables and the COVID-19 conditions to figure out how that mode shifting, or how the replaced modes, the impact of the microtransit modes and how it differs under these different conditions. So thank you. But hopefully I caught us some time there. I'm happy to answer any questions.
Sure did, thank you. Anybody have any questions for Emma? I just had a quick question on your correlation to drive alone between never, infrequent, and frequent. It seemed like you have a U-shaped curve. So
for some of them it did, yeah. So that yeah, and maybe there's there's something unique about somebody who is willing to try something for the first time and then potentially doesn't like something about the mode, and so they only used it once or twice. So there maybe there's something unique about that. But there's other, some of the other ones it was a smoother trend. Yeah.
That's anybody else have any questions? If not, thank you so much, Emma.
Yeah, thank you.
Presentation, which is Maria. So Maria has a Bachelor's of Engineering and a Master of Science in Civil and Environmental Engineering. And she's a PhD candidate in Transportation Engineering at the University of Texas at Austin, and a graduate research assistant at the UT Center for Transportation Research. She's also the UT student chapter president for the Women's Transportation Seminar. Maria?
I think Maria cannot make today. I will show her a pre-recorded video instead.
Okay.
Hello, everyone. Thank you for taking the time to listen to my presentation. I will be presenting about the data analysis of arterial corridors that we developed at the University of Texas at Austin Center for Transportation Research. So this study describes a framework for the analysis of freeway corridors performance using probe-based data. The proposed analysis approach includes two components, one focusing on reliability metrics and one that quantifies delays using atypical traffic conditions. The index data considered consists of average travel times on small freeway segments, denoted XD segments, which are selected through a web interface. Typical travel times were analyzed by time of day in the selected corridor in order to gain insight into travel time patterns. The travel time metric is computed as the average value of total corridor travel time by 15-minute interval, where total corridor travel time year, direction, and type. The average travel time can also be aggregated by time of day, month, direction, and type. And by type we mean weekdays versus weekends. And we also calculated the travel time index, buffer index, and planning time index as part of our reliability analysis. The second part of our analysis is the delay analysis. Our delay analysis started by identifying atypical traffic conditions where travel time is at least 3 standard deviations higher than the average travel time. It is important to consider that volume data has not been incorporated to the analysis yet. Delay is thus defined in terms of average travel time increases and/or speed reductions rather than in vehicle hours. The delay analysis considers the entire corridor, but our framework allows for the analysis of corridor subsections. Our delay analysis metrics include queue position and corridor travel delay in minutes. We also developed maps of the delay ratio and of the delay per mile. We will take also the example of an accident that happened on I-35 southbound lanes on August 20, 2019. In this heat map, we classify time steps based on their distance from the mean measured in standard deviations. The standard deviations were aggregated by hour, minute, and day type, which can be weekday or weekend. After identifying high travel time standard deviations, during atypical time, we performed a delay analysis. The figures in this slide describe queue position by presenting segment speeds over the analysis period in a heat map. The y-axis is the distance between a point and the downstream end of the corridor. Each vertical column shows the variation of speed along the corridor, with each dot representing the position of the start point of a segment with respect to the end of the corridor in the direction of travel. Traffic is assumed to move from top to bottom. Successive columns show the evolution of traffic conditions over time at 15-minute intervals. Red vertical lines are used to connect segments in which the speed is below the threshold used to define a queue on a given time interval. As part of our delay analysis, we also calculated the travel delay, which was computed as the maximum of the actual travel time minus the average travel time, and 0. We also computed the delay per mile by dividing the previously computed travel delay by the segment length. The heat maps in this slide show the delay ratio that was calculated as the delay per mile divided by the travel time per mile. In conclusion, a corridor performance can be assessed using multiple metrics based on the available data. In this study, travel time reliability metrics and delay metrics are computed based on INRIX data. The analysis can be computed for any desired time period, and the purpose of this analysis is to reflect the corridor traffic conditions and assist decision makers and planners in project prioritization and infrastructure spending. And finally, thank you for listening, and please don't hesitate to email me any question that you might have.
I think she had asked for email questions. So with that, we'll come to our last presentation. Our last presenter is Hatem Abdullahi. Hatem is a postdoctoral researcher in transportation engineering at McMaster University. He holds academic degrees from Cairo University, MS in Civil Engineering, Public Works, and McMaster University, PhD in Civil Engineering. His research interests are electric bus transit systems, network science applications in transit, road design consistency and reliability, and driver behavior and human factors. This presentation is about predicting the energy consumption of battery electric buses using open source data. Take it away, Hatem.
Okay. Hello, everyone. I'm here today to present battery electric bus energy consumption framework using open source low resolution data. Before I start, I would like to acknowledge the contribution of my colleagues at the Transit Research Informed Practice Lab. Also, I would like to acknowledge the support grant from NSERC and from the Social Science and the Humanities Research Council of Canada. So I will start with an introduction about the battery electric bus systems. Then I will define the main objectives of this study. After this, I will talk about the energy prediction framework and the performance of the framework. And finally, I will state the conclusion of this work. So implementing battery electric bus in transit systems requires studying the impact of an all-electric fleet on the existing energy infrastructure to get optimal operation scheme and minimizing the total cost of the system. However, minimizing the total cost depends mainly on accurate estimation of the consumed energy during the bus operation. However, in the literature, we didn't find a data-driven model that combine the speed profiles and route topology and passenger loading profile and weather condition all in the same model. Also, there is no framework that can predict the energy consumption using low resolution data and open source data. And also, there is no validation for accuracy of such a framework. So in this study, we are answering two main questions. The first one is, can we develop a framework for the transit planners that can rely on open source low resolution data? And also, what's the accuracy level of such a framework? So the proposed framework starts with collecting open source data and then perform a factorial design to get the possible operation scenarios, and then the modeling step where we can estimate the observed and predicted energy consumption, and finally evaluating the model performance. So to elaborate more on this, so first we collect open source data for 6 bus routes in Hamilton, Ontario, Canada. And then based on the collected data, we get the operation scenarios using fractional factorial analysis. And after this, we use the simulation model to estimate the observed energy consumption. And finally, we use a data-driven model to predict the energy consumption. After this, we perform a three-step validation process to check the accuracy of the framework. So for the open source data we collected, it includes a topology data that shows the location of all the bus stops and the distance between them. Also, elevation data to get the upgrade and downgrade route gradient. And then a weather data and a speed profile that have been collected using AVL data and GPS data. And automatic passenger count data to get the number of passengers amongst bus trips. So after collecting the data, we select the main vehicular parameters such as initial state of charge, bus mass, the frontal area of the bus, operational parameters such as ABC data, spacing between bus stops, acceleration and deceleration rates of the driver, and the topological data such as the route gradient and the route condition, and external parameters such as ambient temperature and air density, and HVAC and auxiliary powers. Then we conduct a factorial analysis in order to get all the possible operation scenarios that can face the battery electric bus during operation. And as a result, we got about 6,048 operation scenarios. After this, and to calculate the observed energy consumption data for the aforementioned scenarios, we used a simulation model that we developed in one of our previous research. And as we can see, the model is developed using Simulink software, where the energy moves from the battery to the motor, and from the motor to the gearbox, and from gearbox to the wheels, and the bus can operate. Also, the HVAC power and the auxiliary power systems are included in the model. So this simulation model is already validated using Altona test real world data and has an accuracy up to 95%. So to calculate to predict the energy consumption data, we used a data-driven prediction model that we also developed in one of our previous research. And this model has a strong linear relationship between the energy consumption and between the selective parameter, including the route gradient, initial state of charge, route condition, HVAC power, passenger loading, the driver aggressiveness and stop density, and average speed. So after this, to check the model performance, we applied a 1-minute single trip validation where we divide each speed profile into a 1-minute drive cycles and validate each minute separately. And as we can see, the 6 bus routes has a goodness of fit above 0.8. Also, we applied the trip validation where we validate the entire bus trip, and it shows that the proposed framework can explain more than 95.8% of the variation happening in the energy consumption rates. And finally, we analyze the error and perform an error sensitivity analysis. And we find that the initial state of a charge has the highest impact on the error. And that's because we didn't consider the regenerative brake in our model. And regenerative brake represents the amount of recovered energy due to using the brake. So as a conclusion, so the validation of our framework shows a powerful goodness of it, and it can explain more than 90% of the variation happening in the energy consumption model based on a trip validation. Also, the mean absolute percentage error shows that the error percentage for all routes used in this analysis is between 10 and 18%. And the proposed data-driven model can inform the optimum operation profile design that can enhance the energy utilization in the battery electric bus transit systems. And thank you.
Thanks, Hatem. Anybody have any questions? If not, my only question is, what are the policy implications of your work?
Sorry, what is the policy work?
The policy implications of the work that you did.
Well, we provide a framework that can help the transit planners to select the best bus routes that can give them the lower or less energy consumption in the routes.
No.
So yeah, that can be used like to select the best bus routes that can be electrified in the future. And actually, currently we are working on developing that works and including like optimization model that can allow us to like have it included in designing the battery electric bus transit systems and implementing it in the public transit network.
Thank you. That's very helpful to know.
Thank you.
So, anybody else has any other questions? If not, you're almost at the end of our session. So thank you very much for your attendance and to all the speakers for showing up and presenting your work. And before I close the session, I see Kara out here. Kara, you have anything to say, anything to add?
Yes, I typed in the chat box, but thank you all so much for being a part of this. We're demonstrating, I think, to other disciplines and certainly to all nations that we can do this. So we're really impressed with the variety of speakers and topics. And yeah, we appreciate all of you being part of it. I know you just went through the TRB paper submission process, so a lot of people are exhausted. And it's a hot summer, August here in Austin. So we're really proud of you. We hope you have a great rest of the summer if you're here in the Northern Hemisphere, and hope to see you tonight for what's her name? Lynette Chia at the university in Singapore. It's like the design university. She's going to be talking about decarbonization of freight. And then that's the headline talk for those tracks. And then, of course, at 10 a.m. Central US time, we've got the Western track starting again tomorrow with Juan de Dios Ortuzar talking about biking and what a great mode that is and why it's not more utilized. So we hope you guys can make it. Thanks for being here.
Thank you, everybody. Thanks, Cara. Have a good evening.
Thank you, everyone.
Thank you. Bye.
Thank you.
Thank you.
Bye.